Hello everyone, this is Dr. INdradeep Kumar, Assistant Professor, IARE, Hyderabad. This is the module 4 of Analysis of Aircraft Structure. Okay, so we are starting the module 4. So in this video, we will see a structural and loading discontinuities first, and then we will see the next test. Okay, so the next topic will be for this video is general aspects, how the closed section will be there and all. Then shear stress distribution at built-in end. That built-in is there of a closed beam section. So we will see shear stress distribution for a closed beam section, and we will see the same thing for the open beam section in module 5. For module 4, we will see the closed beam section, and then we will see idealization of a panel. This is how a panel can be idealized. Okay, so till what we had seen in that one, it was like just for some normal or just you can see simplified structure, we can find the moments, shear stress distribution and all. But by this method, we can go for any other complex structure also is there, or just see you can see in this image itself that complex structure is there. For that type of a structure, we can find the shear stress distribution also. Okay, so just see here. So far we have concerned with relatively uncomplicated structural section. So that uncomplicated structure, okay, which in practice would be formed from thin plate or by the extrusion process. Means either that is having the thin plate or that we just slightly extruded and that form that is there. So while these sections exist as structural members in their own right, they are frequently used to stiffen more complex structural shapes such as fuselages, wings and tails. So once extruded is there, so for that support you can see just here like this stringer and spars are there that are connected here. So see, thus a 2-spar wing section could take the form shown in figure 1, 2 are there, right? Okay, in which jet section stringers are used to stiffen the thin skin. So upper word is called of the skin, that is the skin. So this jet type, okay, the stringer is used there. Okay, the thin skin, while angle section form the spar flanges. So this is here your stringer, and wherever the angle is there, that is the spar flanges. So these are the spar flanges is there in that one. Clearly, the analysis of section of this type would be complicated and tedious unless some simplifying assumptions are made. So now calculation of this is tedious, or you can say complicated. So for that, what we will do, we will assume something, right? So some assumptions is required. So after some assumptions, what we will do, we will simplify this structure and then we will solve. So generally, the number and nature of these simplifying assumptions, just here, nature and number of these simplifying assumptions determine the accuracy and the degree of complexity. This according to how much we assume, right? According to that only we will get the accuracy of the whatever we found and degree of complexity of the analysis. So how it's a complex, based on that only, according to that we have to assume. The more complex analysis, the greater the accuracy obtained. If that as much as more complex analysis will be there, that much greater result will be accurate. Okay, so for this we will see, first we will see the general aspect and then we will go for the second topic was that is idealization. So how to idealize this one? This ideal means what? Almost near to that same thing. So after assumptions, what we will do, we will idealize this structure, okay, and then we will solve for that one. Okay, so let's see. The degree of simplification introduced is governed by the particular situation surrounding the problem. So degree of simplification, how many times we can simplify, okay, that depends on what? Particular situation like surrounding of the problem. So how problem is there, like a stringer is connected, a spar is connected, or whatever things, or how many stringers are connected. So surrounding of that problem is there. For a preliminary investigation, speed and simplicity are often of greater importance. So see, speed and simplicity are often greater importance than extreme accuracy. So instead of finding the extreme accuracy, what we are focusing on is speed and simplicity. Okay, so on the other hand, a final solution must be as exact as circumstances allow. So maximum, or just in simple word, you can say the maximum that accurate answer value should be there. The solution should be maximum, whatever the maximum possibilities are there up to that level. Complex structural section may be idealized into simpler. That is the mechanical model. from which behave under given loading conditions. Whatever the loading conditions are there, in that they are in the same or very nearly the same was the actual structure. Means either we can go for the same one, or if it's not, then by some assumptions very nearly close to the same actual structure, or whatever the actual structure are there, very close to that one. We shall see, however, that different model of the same structure, just here, different model of the same structure are required to simulate actual behavior under different system of loading. So same structure but with different condition we are simulating to get the different system of loading, is different loading time. Okay, so now what do you see for the shear stress distribution or at a built-in end of a closed section beam. So now this is for the closed section. Okay, in the wing section, figure 1, that already this one, right here, this figure. So where the stringer and spars are there. So for that we will see. Okay, the stringers and spars flanges have a small cross-section dimension compared with the complete section. So now what we assume, that having very small cross-section compared to the whole structure. Therefore, the variation in stress over the cross-section of a stringer due to, say, bending of the wind would be small. Since their cross-section itself is small, so that bending also would be small compared to the whole structure. Furthermore, the difference between the distance of the stringer centroid and the adjacent skin from the wing section axis is small. So there also, whatever the axis of the stringer or this will be there, that will be small. It would be reasonable to assume, therefore, that the direct stress is constant over the stringer cross the section. So these are small, so that's why again, like assumptions, we are assuming that over that stress will be again that also constant. We would therefore replace the stringer. So is that what stress is constant, that midpoint of that skin also is that constant, right? So after that only what we are, so instead of that we are just replacing to make like a center of that spar and a stringer. So thus we would therefore replace the stringer and spar flanges by concentrating of area. That's right, because at the center, so now whatever, suppose this size is there and here is the center, so just concentrate all area here, okay, at this point only, and just use this point known as boom. So all that concentration, or here you can see, suppose the stringer was like this, yeah, right? So wherever it's there, so almost it will be here like this. So at the center only we are assuming that the whole area is concentrated, okay, and this whole area, that what we have taken that as concentration, this dot, that the see, that dot is above and below of this line, so that dot is called as booms. What we assumed, that the overall this area, so that is named as boom, over which the direct stress is constant and which are located along the midline of the skin. So that is along the midline of the skin as shown here in figure 2. So this is called the idealization of a wing section. So wherever stringer spars are there, just remove that stringer and spars and put what, the boom there. So as many as the stringers are there, just put spars are there, put that many what, this boom. Okay, shear stress distribution, again that is the continuous. So in wing and fuselage section of the type shown in figure 1, it is given that the stringers and spar flanges carry most of the direct stresses, while the skin is mainly effective in resisting shear stresses. So that is the flanges and spars carrying most of the direct stresses, and what skin is doing, skin is resisting the shear stress, although it also carries some of the direct stress. So shear stress is resisting only, but it's carrying some amount of direct stress. The idealization shown in figure 2 that we are seeing here, this is the idealized one, right? After putting that stringer and spars in the form of booms, that is called only idealization, right? So direct stress carrying capacity, okay, of the skin may be allowed for by increasing each boom area by an area equivalent to direct stress carrying capacity of the adjacent skin panel. So see here, the direct stress carrying capacity of the skin, how much that can be allowed for by increasing each boom area. So just increase the boom area. After increasing boom area, what happened? By an area, how much you can increase? Area equivalent to the direct stress carrying capacity. Up to that, how much direct stress carrying capacity is there? According to that, just increase that one of the adjacent skin panel. So whatever the adjacent skin panel is there, how much they have capacity to carrying direct stress, just increase by the same amount of boom area that boom area will also have the same capacity of direct stress. The calculation of these equivalent area, these equivalent area will generally depends on initial assumptions as to the form of the distribution of direct stress in a boom or skin panel. So it depends on what? Initial assumption is what? From form of the distribution of direct stress. So how direct stress is distributed? According to that, in the boom or panel. So based on that only the starting assumptions will be there. So now this is important for idealizing the panel or any given structure. So suppose that we wish to idealize the panel of figure 3a. So let's see here, figure 3a. So this structure is given. So here some having thickness, okay, and this side also thickness. So this is the length is here b, and this is a, and TD is the thickness here. Okay, so this we have to what? This is the general one, and this we have to idealize in this figure. Okay, so this is actual and this is the idealized one. So how to idealize this figure? Just see here. Okay, into a combination of direct stress carrying boom and shear stress only carrying skin. So the direct stress is carried by boom and shear stress by skin. Okay, as shown in figure 3. So now just see after idealizing here where that is there. So now this is your B1 where the sigma 1 is acting, here sigma 2. Now after idealizing what happens? This TD, that thickness of becomes 0. So TD equals to 0. Okay, so now along this, okay, B1 will act, and along this the B2, so that direct stress sigma 2 will act. Okay, in figure 3 the direct stress carrying thickness TD of the skin is equal to its actual thickness T. So TD, direct stress carrying thickness, should be equal, that is equals to what? The actual thickness T. While in figure 3b TD is 0. So in this figure TD is the actual thickness, whatever the thickness is there, but here TD is 0, that actual thickness becomes 0. Okay, suppose also that the direct stress distribution in the actual panel varies linearly from an unknown value sigma 1 to an unknown value sigma 2. That value also varying from sigma 1 to sigma 2. So sigma 1 is here, so from here to here it's varying. Okay, sigma 1 to sigma 2. So let's see here, from here to here, right, here sigma 1, and like this it's a start varying, here sigma 2. Okay, clearly the analysis should predict the extreme of stresses sigma 1 and sigma 2, extremes of. So just see at extreme only, at this sigma 1 is there, and at this extreme sigma 2 is there. Although the distribution of direct stress is obviously lost, so direct stress distribution would be there. Since the loading produced the direct stresses in the actual and idealized panel must be same, right? Loading that already we have seen that we can go for the nearly to that only, means loading should not change. We can equate moment to obtain expression for the boom area. Now what we will do, just equate the moment so that we will get the boom area B1 and B2. So what is B1 and B2? This is the boom area, okay, B1, and this is the boom area B2, that we have to find. That's taking moment about the right hand edge of the each panel. So just take moment about right hand edge. So after taking moment, what we will get? Sigma 2, that is force. TD into B by 2 is the area of half of that one, and where it's acting, moment into perpendicular distance. So perpendicular distance will be B by 2. Now the difference of that one is half sigma 1 minus sigma 2 TD into B into 2 by third B, where it's acting, that at the center of gravity from opposite side. So and that is equals to what? This second side. So that is sigma 1 B1 B, right? Now from here we have to find B1. Okay, so what we will do, B1 will be what? So see what we have, sigma 2, okay, T D B square by 2 plus, let's see, I'm just multiplying everything here, right? So then it will be easier to cancel. So 1 by 2, then 1 by 2 sigma 1 into this whole thing. So sigma 1 into TD into B into 2 by 3 B, that minus, okay, half sigma 2 TD B into 2 by 3 B, that is equals to sigma 1 B1 and B, right? Now collect the sigma 2 term. Okay, so we are collecting sigma 2 Okay, let's see sigma 1 minus sigma 2. So here sigma 2 is there. So just take these two. Okay, so now sigma, what happens? Sigma 2 TD into B square by 2 minus 1 by 2. Okay, and 1 by 2, and this is so 2 by 6. I'm just multiplying this 2 and 2 by 3. So 2 by 6. Okay, sigma 2 TD into B square. Okay, so first and then plus half sigma 1 TD into B square into 2 by 3. Right, now take the LCM and simplify. So LCM will be here 6. Right, so 6 TD square. Okay, minus 6 sigma 2, or just LCM. Okay, so simplify 6. LCM will be 6. So 6 sigma 2 TD B square by 2 minus, for this one, 2 sigma 2 TD B square by 6. Okay, I'm just simplifying first this term. Okay, then later this we will add. So 6, this whole thing is same. 6 minus 2, so 4. So 4 by 6 I'm just writing here. Okay, then what? So 4, I'll just take here, right? 4 sigma 2 TD B square by 2 plus, now I'm writing this term, half sigma 1 TD B square into 2 by 3. So this 2 by 3 and this 2 by 3, that becomes 2 by 6. Take 1 by 6 common. Okay, now just I'm taking, and that is equals to sigma 1 B1 B. Right, so this is equals to sigma 1 B1 and B. Okay, now just take 1 by 6 common. So after taking 1 by 6 common, and what is common here? T, D and B square. Right, T, D and B square is common. So this won't be there. So T, D and B square common. Right, after that what is left here? 4 sigma 2. Right, 4 sigma 2 plus 2 sigma 1. So 4 sigma 2 plus 2 sigma 1. Okay, and that is equals to what? Sigma 1 B1 and B. So this one B, one B cancel. B1 we have to find. So just take 2 common from here also. Okay, or just from this we can find. So after this B1 will be what? Equals to T B into B by 6. Okay, this is sorry, here this will be 2. So here this will be sigma 2, sigma 2 and sigma 1 after taking 2 common. So divided by B. So what happened after that? We will get sigma 2 by sigma 1 plus 2 sigma 1 by sigma 1. So sigma 1 cancel. So now from here what we will get? B1 equals to TD into B by 6 into sigma 1 by sigma 2. Sorry, sigma 2 by sigma 1. Sigma 2 by sigma 1 plus 2. Right? So this is there. Similarly, we can take moment about this one. Just here in this where we have taken from the right hand. Now take moment about, that's why that B becomes 0. Right? From the right hand. Now take the moment from the left hand. That time B1 will be 0. Similar equation we will get for the sigma 1. So similarly you can find for B2 equals to TDB by 6. Just see the difference is there. When we are finding B1, then sigma 1 is at the bottom, the denominator. When we are finding B2, sigma 2 will be in the denominator. That's all. Everything will be same equation, just we have to divide. That's all. So this is the boom area of first B1 and B2. Clear? Now, so just see how to do that one. Suppose that an open or closed section beam, that this is a continuous of this one. Right, this is just idealization of panel, that is the continuous of this one. That's why I added the headings. Okay, so Suppose that an open or closed, or you can just write here that idealization of that beam is there. Same. Let's see here the topic. Idealization of panel. So that idealization of panel will be continuation of, this is the continuation of idealization of panel. This is the continuation. Okay, and this also is idealization of panel. Continue. Actually, these are continuous. That's why I didn't put the slides heading. Okay, so that are same. Just see that we had seen now how to that we just found the area, that B1 and B2. Now for the next process, so what we will do? Suppose that an open or closed, anyone. So for closed and open, it will be same. Just for the closed one, that open one, when we have to remove the wrapping, on that we will see later. Closed section beam is subjected to given bending or shear load, and that the required idealization has been completed. So after that, after applying the shear load or bending, whatever is there, that idealization completed. Now after idealization, what happened? So just see, the analysis of such section usually involves the determination of neutral axis position. So that's what we have to do. First, determine the neutral axis position and the calculation of sectional property. So once determine neutral axis position and then calculate the sectional properties. What properties? So just see, the properties of the neutral axis is derived from the condition that the resultant load on the beam cross section is 0. So where the resultant load on the beam cross section will be 0, that will be the neutral axis position. Hence this one, that over the area, this stands for area, means over the entire area whatever is there. So that sigma z into dA, that equals to 0, or you can say stress into A, that is the force, right? That how much load is acting. Okay, that must be equal to 0. That's why here it's the mention, the resultant load. So that is the load only. That load must be equal to 0. So at the point at which the load will be 0 and in the cross section, that will be the neutral axis position. The area A in this expression is clearly the direct stress carrying area. So this area is direct stress carrying area only. It follows that the centroid of the cross section is the centroid of the direct stress carrying area. Yes, it follows the centroid of the cross section is the centroid of the direct stress area. So we have taken that one and that area is this one. So both will be same, is direct area of centroid of the cross section what we are taking, and centroid of the direct stress carrying area, that also same, depending on the degree and method of idealization. So how many degree you are idealizing and what is the method of idealization, that depends on that one. The sectional property, that IXX, that's here it was there, the sectional property after that cross section. So that's why the sectional property IXX and so on, like IXX, IYY, IZZ depending upon the axis, must also refer to the direct stress carrying area. So along IXX, that is the direct carrying stress. So if Y is there, then IYY also will be the direct carrying stress. Okay, so now indirect stress distribution, that's now bending of open and closed section. So just here I am combining, later we will see again for the closed one. Okay, so this is just for okay, or you can see just for the closed beam section. Indirect stress, because this property is same for both, that's why I just skipped here, but we are still in closed section. Okay, in open section again we will see that one. Indirect stress distribution, the coordinate xy of points in the cross section are referred to axes having their origin at the centroid of the direct stress carrying area. So already we had seen that xy coordinate and having centroid at the origin of that, origin at the centroid of that will be there. Furthermore, the section properties, that is IXX, IYY, IZZ, IXY, because two dimension is there, so IXY or IYX, both will be same, are calculated for the direct stress carrying area only. So whoever is carrying the direct stresses, for those only we have to find what IXX, IYY and IXY. Okay, in the case where the beam cross section has been completely idealized into direct stress carrying boom and shear stress only carrying panel. So now shear stress will carry only panel and what direct stress will carry by the booms. The direct stress distribution consists of a series of direct stress. So let's see the distribution that consists of series of direct stresses concentrated at the centroid of the boom. So now what we are considering, the direct stresses are concentrated at the centroid of the boom. Okay, so here That is the first video over. So if you have any doubt, or just once again I am just recalling. Okay, there. So now what we will see? We will see for the what? Structural loading and discontinuities means how the closed section or wherever the difficult or complicated structure is there, then how to find. So that we had seen what in this one till last time. So if this is the complicated structure having the stringers, the spars, right? In that how to simplify that area, how we will find the shear stress distribution. For that, what we have to do first, we have to go with the idealization of this figure. Idealization means what? Ideal means almost near to that equal, but that is not exactly. So as much as we will assume our that accuracy will get that much affected. So that our accuracy should not get that much affected. According to that only we have to simplify this one and then we can calculate. So for simplifying what we have to do is just whatever the stringers and spars is there, okay, just replace with the boom, okay, that boom. Why? Because the stringers and spars are comparatively less, this area is very smaller and hence the center of gravity also will be at the very small. Suppose this already this was size is there, somewhere here is there, that also is very small compared to this one. So what we are doing, because of that a small area, those will concern that carry the direct stresses. So that's why for this one, all the stringers and spars, we are just replacing the boom wherever these things are there. Just replace that with the boom that carry the direct stresses. Okay, so first and carry just replacing of this one is called only the idealization of this one. So these are what just general aspects that already we had seen. So here after coming this one, next what is there? So wherever the stringers or spars are there, just see here that is replaced by the boom. Okay, and that boom must have their center along the skin of this one. Okay, along this line, their center should be there. Okay, with that now we have to find. Okay, so what that will carry the direct stresses, that boom. Okay, now the thing how to find the boom stress or how to idealize. So for that the figure 1 is there. So now this is the figure 1. Okay, so or you can just assume this is the question or this you have to idealize. For this you have to find. So first what we will do, first we will idealize. So in actual one, this having the TD, that thickness, okay, containing the direct or having the direct stress, here it's experiencing, okay, actually TD equals to T, some thickness of this one. Once we will idealize, means what we are there, we have seen that in a stringer also, this was there, right, and for this we are just substituted, this was the cross section. So this goes along this one, right, in the second figure here, let's see, this was showing in this figure, okay, so this is the cross section of that one and inside that will goes like this wherever whatever the length of the skin will be there. Okay, so here in this case after idealizing what happens, this TD, the direct stress containing that thickness will be 0, only along the boom that direct stress will act. So now for that we have to find first what? Boom area. For finding boom area what we have done, okay, just take moment along for first time, moment along this one. Right, so taking moment along this one means B2 will be 0, find this one, the total moment, this one, moment is what? Force into perpendicular distance. So sigma is the stress, sigma into area will give you the force into perpendicular distance. So sigma into TD into B by 2 will be the area. So sigma into area will be the force, right, and B by 2 will be the perpendicular distance. So this will be the moment. Similarly, again sigma 1 minus sigma 2, the resultant, because the C here, you can see this one, or just here, divide this one. Okay, so for this rectangular part we found, that is here. Okay, now for this triangular we have to find. So here is the sigma 1, from here to here sigma 1, but up to this only sigma 2 is there. So what will be the difference? This one from here to here, this will be sigma 1 minus sigma 2, right, for this area. For rectangular we found here, right, for now this triangle. Okay, so sigma 1 minus sigma 2 and TD will be this one, TD into B will be the area where this will act. For the triangle it's acting from this side, so it's acting at 2 by 3rd, that at center of gravity already we had seen, at the center of that gravity we have to find. So 2 by 3 of B. So this is the moment because of this triangular load, that must be equals to what? Sigma 1 into B1, so force B1 into B, whatever the boom area into this B, that will be, and sigma 1, so sigma 1 into B force. So now after equating that sigma 1 into B1, that boom area is the force and B moment because of the moment, not B moment. Force into perpendicular distance. So B is here, just here. This is perpendicular distance. So this is moment. After equating, just simplified. I already showed you how to simplify, right? So B1 will be equals to what? After solving, B1 equals to TD into B by 6 into 2 plus sigma 2 by sigma 1. So here one thing you have to remember how to simplify this one or how to. Similarly, you can find for B2 also. Just now for B2 finding, you have to take moment along B1. For finding B1, take moment along B2. For finding B2, take moment along B1. Okay. Same way you can find. So after this, just see a B1 is there. So B1 carrying the sigma 1 stress, right? So that for B1, sigma 1 will be in denominator. First term will be 2. Everything is common. Only these two terms are different. Sigma 1, sigma 2 by sigma 1 and here sigma 1 by sigma 2. So for that, what happens? For if B2 finding, means B2 carrying the stress will be denominator. So whatever the boom area you are finding, containing that boom area stress will be in the denominator and the other one will be in numerator. So similarly, you can find B1 and B2. Okay. So after that, once we find the boom, then resultant for the equilibrium, what should be there? Right? That already we had seen for the cross section, that neutral axis, where all the forces that will be 0. So for finding that one, what do we require? Resultant load. Resultant load where that it's acting at the center of the gravity. There that will be 0. And through that only the neutral axis will pass. Means that will be the neutral axis position. So force, sum of force in that area. This A means over the entire area. So force, that is sigma 2 into area is force. So force into that force must be equal to 0. At the point where the force is equals to 0, that will be the point of neutral axis position. Okay. So just like a stress carrying, then sectional property we have to find depending upon how that is there, that Ixx and Iyy. So here just see the furthermore sectional property Ixx, Iyy and then Ixy is required to find. Okay. So whatever the direct stress concentrated is there, where that is centroid of the boom. So direct stress distribution, this is important point to remember. Direct stress distribution consists of a series of direct stress concentrated at the centroid of the boom. So it's not necessarily only one. It may be more than one. This figure itself we had seen, right? Here. So if you rectangular load, then this load. So many loads are acting over all of this load. We have to consider, and where we consider that at centroid of the gravity, and that's why we have taken here for in this case B by 2 for rectangle, and for triangle 2 by 3 B. We have taken this one. So just whatever the number of loads acting, just we are considering that as that is acting at the center of gravity or centroid, right, of the boom. Okay. So this is your reference. That. Okay. So just go through this one. Okay. With that, if any. And for this, you can refer also the Maxon book. Okay, Maxon 4th edition that you can refer. So if you have any doubt related to this, you can just comment on the video or you can contact me related to your doubts. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.